Bismillah ar-Rahman ar-Rahim. Today we are going to start a new unit which is about Carnot map. Okay, and this is the outline for this unit. Okay, first we will answer the question, why do we use K-maps? Why not just algebraic manipulations? Or because K-maps are used for simplification. Okay, why just not have the algebraic manipulations or simplification? That's enough for us, but K-maps can give us more than that. Okay, as we will see. Then we will introduce K-maps, 2, 3, 4 variables, and then talk about implicants, prime implicants, and essential prime implicants. Okay, then we will discuss how to do how to obtain a minimum SOP or POS using K-maps. Okay, and then how to handle don't care conditions, and then give you just a demonstration of how to do a 5 or 6 variables K-map. Okay, let's get started now. So the question is, if K-maps are used for simplification, okay, and we have already learned Boolean algebra and how to simplify functions using Boolean algebra, why is that not enough? Okay, first of all, the method of algebraic manipulation and simplification of functions using algebraic manipulations is not systematic, and it's very difficult. Okay, and it depends on the experience. Okay, on the experience of whoever is doing it. Okay, and also it doesn't give you any clue of what the minimum number of literals is. Okay, you have to, for example, if you see the consensus theorem for the first time, you will never think that the consensus term is redundant. Okay, because it's not apparent to you. Okay, so it is very difficult to the bottom line here is that algebraic manipulations are good, okay, but they are difficult, and it is not easy to see if we are already at the minimum expression or not. Okay, so the K-map, on the other hand, is a systematic approach. The K-map, so it's called Carnot map, okay, or for short K-map. Okay, K-map method, simplification method, is a systematic approach, okay, to simplifying Boolean functions to minimum standard forms. Okay, and you can think of this as the motivation line for our lesson about K-map. Okay, so if you want a systematic approach for simplifying Boolean functions and finding the minimum, guaranteed to find the minimum, okay, then you should study K-maps. Okay, all right, let's move on. So Carnot map, or K-map for short, is basically, you can think of it as a very simple rearrangement of the truth table into a rectangular grid. Okay, this is very important to understand. K-map does not add any information to the truth table. It is actually a truth table in disguise. Okay, it is a truth table but in a different form. Okay, so we rearrange the truth table cells, okay, such that it satisfies our requirement for the K-map. Okay, so the rearrangement of the table, of the truth table, should be done such that adjacent squares in the K-map are different by only one literal, exactly one literal. Okay, so this means for us that the input patterns of adjacent squares differ by exactly one bit. Okay, so you will have, for example, input pattern, for example, in the truth table, if your input pattern 0, 0, 1, okay, should be adjacent somehow to 0, 0, 0, okay, because they differ by 1 bit, which is the least significant bit here, okay. So we need to find a way to group or to rearrange the cells, the output cells of the K-map, of the truth table, such that all the cells have adjacent which are different only by 1 literal or 1 bit position. We will see examples of that. So here is an example. So here, suppose that I have this function here. Notice that I'm giving A as input, okay, and B as input, as another input, okay, and then F, okay, but I'm giving it in a symbolic form here, F00, F01, F10, F11. So this is, for example, this is the value of F when the input is 1, 0, okay? All right. So if I want to transform this into a K-map, it's called a 2 variables K-map, okay? Then I do it this way. Why this way? This way here, okay? Why this way? Well, because F0, 1, you see the input 0, 1 here, okay? And the input here is, I'm sorry, it's 0, 0 here, okay? And the input here is 0, 1. So they are different by 1 bit here, and they are adjacent, okay? Here, it's F0, 0 and F1, 0. They are adjacent because they are different by 1 bit, okay? And here, again, 0, 1 and 1, 1. They are different only by 1 bit. And here also 1, 0 and 1, 1, okay? And this can be achieved by partitioning the truth table variables by having A going vertically down, okay, from 0 to 1, and B going horizontally from 0 to 1, okay? So this cell here is when A is 0 and B is 0, okay? So this is F00 here, okay? A0 and B0, okay? So this way, we just placed every adjacent square with its true adjacent, okay? With another square, we placed adjacent square together, okay? Notice that this square here is not adjacent to this, because here both A and B changes, okay, from 0, 0 to 1, 1, okay, from 0, 0 to 1, 1, okay, so 2 bits are changing, so that's why these two are not adjacent here. Similarly, for these two are not adjacent, so 0, 1 is not adjacent to 1, 0. 2 bits are changing here, okay? So these bits are the input bits here, okay? So we care about, so the definition of adjacency is with respect to the input pattern, okay? So let's take a concrete example now and see why is the adjacent property rearrangement into adjacent cells help us in minimizing Boolean functions. Okay.
Doctor.
Yes.
What do you mean by input pattern when you said adjacent depends on input
pattern? 0, 0. This is a pattern. 0, 1, another pattern. 1, 0, a third pattern. 1, 1 is the fourth pattern. Okay. So this is the value of F when A, B are 0, 0. I'm denoting it here by F00, 0. Okay. And this is the value of F when A is 0 and B is 1. Okay, so I'm denoting it by F01 and so on and so forth. Okay, you get that?
Yes, I get it. Yeah.
All right, so now why do we put adjacent cells next to each other? Okay, because we want to take advantage of that by taking common factors to reduce the number of literals. F both, of course, if both squares have 1, if both adjacent squares have 1. Okay, now this is an example, and we are officially here starting the two variables k-maps. Okay, so suppose that f is the sum of these minterms, 0 and 2. Okay, now I'm numbering the squares here. Okay, 0, 1, 2, 3. Why is that? So 0, this 0 means that this is the row number 0 of the truth table. It's because A is 0 and B is 0. So this is row number 0. Okay, this is row number 1, 0, 1, 1. And then row number 2, it's 1, 0, 2. Row number 3, which is 1, 1. Okay, 3. So my F is 0, 2. Okay, and so I put a 1 here. Okay, and a 1 here. Now my F is given in a numeric form, not a symbolic form like this one here. Okay, it's not a symbolic anymore. So my F is given in a numeric form here. Okay, so I have a 1 here and a 1 here, and it is implied that these two cells are empty or blank, so it is implied that they have a 0. They have zeros. Okay, so now let me ask you this one here corresponds to M0, right? M0, and this one here corresponds to M2. What are the algebraic expressions for M0 and M2? Okay, M0 is nothing but a complement, B complement, right? And M2 is a B complement. Remember how to do that? Do you still? You should
Yes.
you should be prepared for the quiz, right? Yeah.
Yes.
Yes.
So using algebraic manipulations, okay, we can simplify this, okay, which is basically a B complement ORed with a complement B complement, and you can take a B complement as a common factor, and by the complement property and identity, we have B complement here. Okay, so notice that I get B complement. Why? Because both of my minterms are in the region where B is 0. Okay, and why did I get rid of A? Because A, okay, is really changing between these two ones here. So it is changing from a complement to A, okay? And this allows me to take common factor B complement, and this will result in a 1 after I take the common factor, okay? So if I draw the K-map again, okay, and do it completely using K-map, then what I do is that I have 1, 1 here, and then I group these two ones together, okay? And I notice that since B is 0 in both the ones in both the minterms in the group, okay, it will show up in the expression, okay, but it has to be complemented because it's a 0 here, and since A is changing from 0 to 1, it will be dropped from the expression. It will disappear. Okay, so my F is going to be B complement here. Okay, so this is how we use K-map to simplify this function here. Okay, so we just combine these two. Okay, and the net effect of combining them is to take common factor and then get rid of the variable that is changing from 0 to 1. Okay.
Doctor.
Yes.
If the function was given in terms of a max term, would be interested in zeros.
Not yet. This is a subject that we will cover later. When we talk about product of max term, product of sums. Okay. Right now, just consider the case of minterms. Okay.
Okay, sure.
Yeah. But it's a similar concept. We'll see later that it's nothing. There is nothing special about it. Okay. But believe me, if even if I don't teach you, okay, I teach you only the sum of products, you should be able to derive a way, okay, to do the product of sums itself using the
I
model.
just wanted to ask, we would be interested in zeros in the K-map only, right?
Of course.
It was in max term.
But then if you take the complement of this function, what happens?
Oh, yes, that makes sense, yes.
Yeah, if you take the complement, then you're
Yes.
working on the complement and then complement the complement. Yeah.
Yes, I get it now.
All right. So, but later we will cover this in details, inshallah. So, what if more than one group can be combined? Okay. We do the same, and then we OR the products that we get. Okay. So this is an example here. But notice that each group has to be in rectangle. So this is for all the K maps that we have. Okay, this is an important thing to remember. Okay, pay attention if you haven't paid attention so far. This is the right time to pay attention. Okay, a square or a group in K map like this one here, it must be or must satisfy two conditions. The number of ones that you group is a power of 2. It has to be a power of 2. That's number one. Condition number one. Condition number two, both of the conditions must be satisfied. So power of 2 is first. And the second condition is that it has to be of rectangular shape. Okay? You cannot like, first of all, can I take, using these two rules, can I combine these three together?
No.
No, why?
Rectangular. It's not a power of 2.
It's not power of 2 as well as it's not rectangular. I violated both properties here. Okay, so it is not going to work if you take, for example, 3 min terms together. Okay, it has to be a power of 2. For example, 4 is fine. 2 is fine. 1 is fine because 1 is 2 to the 0 as well. Okay. But what we do is usually we take the largest power of 2 in a rectangular form that we can form. Okay. Otherwise, if we don't take the largest, then we will not wind up with a minimized function. Okay. So here is an example. So we have this function here is the sum of these min terms 0, 1, 2. So I draw my little K map here, and this is min term number 0, min term number 1, and min term number 2. So what I can do is that I can group these two together, and we have seen that this is B complement. Okay, and this one here is going to be what? Is going to be a complement, right? Why? Because the B is changing, so it should disappear. Okay, in the green rectangle here, the B is changing from 0 to 1, so it should disappear, and the A is 0, so we complement it. So my F in minimal form is a complement ORed with B complement. Let me ask you, and for the sake of review, let me ask you, what is F in product of max terms?
It will be 3.
3, excellent. And what is 3 in algebraic form? Max term number 3. What is it?
It will be A.
It will be
A plus B.
A complement.
A complement B.
Yes.
Can you relate this to this now? It is the simplest form of F. Okay, it's already the simplest form of F. This is a max term. However, it's also a sum of product as well. Yeah. So these 3 products, okay, the minimum form of these 3 products is this sum of product. Okay. So yeah, I mean this makes sense, right? So instead of 1, 2, 3, 4, 5, 6 literals, you wind up with 2 literals. Okay. So let's do a validation now. Okay, let's perform Boolean algebra to do a validation. We still have 4 more minutes, so yeah. So what is 0, 1, 2? Min-term number 0 is A complement B complement, ORed with A complement B, ORed with A B complement, right? Then you can take A complement as a common factor between these two. So you'll get B complement or B, ORed with A B complement, right? So this goes away. This is by the distributive law, and then this is by the complement and identity, and this is by simplification property. Okay, and then you get the same result here, but with smaller effort. Okay, all right, any question?
Yes, doctor.
Yes.
When you did the first method, can I say if the other canonical form has less indices, it will give me a shortcut like we did here with the maxter instead of going to the K-map? So I would change to the other canonical form with lesser indices and then do algebraic manipulation with it. Or it would be ready like this, like.
Yeah, but this is an ad hoc method. Okay.
Okay.
It's not a systematic method. Okay. Because yes. I mean, what I mean is here is that you don't guarantee that. Okay. It's not always true, maybe. Okay.
It's a one-time thing.
Yeah, you have to make sure by drawing a K-map. So always safer to draw a K-map and then find out the minimum and make sure that it is indeed the minimum. Okay. All right. Yes. Let's move on to 3 variables K-map. Same idea applies. Okay. Let's take an example. So we have f here. That is of a function of ABC, okay, and then it is the sum of these min-terms 0, 1, 5, 7, okay. So first of all, this is a plot of the K-map. First of all, how do you construct the K-map of 3 variables? Okay, it's like this. So we have the A that goes from 0 to 1 from top to bottom. And then we have BC, okay, together. Okay, the BC are going to be 0, 0, and then 0, 1. And then instead of 1, 0, I'm going to have 1, 1. Because remember, adjacent cells must be different by only 1 bit, okay? Otherwise, if I put 1, 0 here, then 2 bits will be different, okay? And then finally 1, 0. This is called the gray coding. Okay, the gray coding guarantees that adjacent cells differ by a single bit. Okay, now you can number the cells, the min-terms here. So this is 0, okay, because 0, 0, 0, and this is 1 because this is 0, 0, 1, and this is 3 because this is 0, 1, 1, and then 2, which is 0, 1, 0. Okay, so the numbering goes 0, 1, 2, 3, and then 4, 5, 6, 7. Okay, so the ones here are going to be, or the min-terms are going to be here and here, depending on the number here. Okay, and here and here. We'll pick up next time. We will continue this example, inshallah. I think it's a good place to stop here, okay, and switch to the quiz. Let me stop recording.